Yeah, so actually, with respect to the president's here today, so you can see I'm showing my American colors in my head. Either that or I'm a New England Patriots fan, but I'm not. So anyway, so it's just by chance. So I'd like to talk today about securing the Internet of Things. And hopefully by the end of this talk, it'll be clear why this is of intense importance to data science. So what's the Internet of Things? It's this basic idea that we're going to see computation, sensing, and communication integrated not just in our laptops and our phones, but into everyday objects and places. So we're going to have things like the Nest thermostat, smart thermostat, digital picture frames. Down on the bottom right, this is a shirt that came out this summer that actually has embedded sensors. And it's that, well, you work out, it can measure all these properties of your body. There's a little computing module down on the waist, which then can send out the data. Things like fitness trackers, the Basis watch, these sole inserts for your shoes, smart refrigerators, smart light bulbs that you can actuate from the internet. This idea that we're going to see sensing and actuation integrated into physical objects and everyday life. So that's the Internet of Things. And we all know it's going to be a complete security disaster. Like, we all know this. I mean, people have been writing about this for almost half a decade now. These are all some just recent points. In the same way the web was, when it first came out, a security disaster. Like, we see the 5,000 car pileup up ahead on the highway, but yet it doesn't seem like anyone's doing anything about it. So, for example, just this summer, HP's security group conducted a survey. They took 10 IoT devices, just things like TVs and smart picture frames, and looked at their security properties. 90% of them had some sort of security flaw, whether it was privacy concerns or poor passwords. I mean, 70% of them didn't have any encryption, right? Didn't encrypt any of the data they sent. So anyone nearby, if your TV is over Wi-Fi, could observe what it was sending. 60% of them had insecure updates, which means that you could, if you were sitting next to that TV when it was doing a firmware update, you could masquerade and you could reflash it with whatever program you wanted. So this is the level of security that we're seeing in these things. And so people are writing all these articles about how the Internet of Things, it's going to kill you, right? Somebody's going to hack your door lock, or it's going to hack your medical device. And we all know this is happening. So the Secure Internet of Things project, this is a 5-year project that we're just starting now, part with the help of SDSI. And it's a collaboration of multiple universities. Currently there's 12, now 14, because we've added 2 more, which is great, faculty collaborators. And our goal is to rethink the Internet of Things, how their systems are built, how their software is built, and how applications are built from the ground up. The goal of securing these systems, to make the Internet of Things something that we can depend on and can trust, rather than something which is a persistent security problem and a threat. And so kind of a high level, like, what's our goal? It's to make a secure IoT application as easy as a modern web application. Today, you want to develop an IoT application, it's a lot of effort. So think the web in like 1994, 1995. I was at the Maker Faire last summer, and I was talking with this man who owned a company they were building a smart watering system for your home. And to have a couple soil moisture sensors that stream some data to the cloud and then control your sprinklers, it took 10 engineers 2 years to build this application. And I did not have the heart to ask him whether it was secure, right? Because I knew it wasn't. And so sprinklers might not seem like a huge security threat, but you can imagine things like door locks, or actually irrigation at the farm scale. Like today, somebody breaks into a system and they steal some credit card numbers. Right? Tomorrow, they flood a field, or as happened last year in Germany, they cause a blast furnace to melt down. And so this project, there's a bunch of faculty researchers, and we have grants, et cetera. But I think one of the big parts is this this flagship project grant from SDSI, which is helping us take the first steps towards this project. OK, so what's the Internet of Things? You hear people talking about it all the time. It seems confusing. It's everything from smart shirts to smart industry. And I think that that confusion is warranted because today it's very much a marketing term. And when people use it, they mean 4 very different classes of systems that have very different security and systems challenges, and very different architectures and very different problems. And so when they use that term, they could mean any one or more of these. And so it seems very vague. So, for example, people talk about the Internet of Things as industrial automation, that I'm going to instrument all aspects of my petroleum processing plant at very fine grain and stream this data out to maximize plant efficiency. Or I'm going to instrument my automobile manufacturing floor to do predictive maintenance. Now, these kinds of systems, they're in a controlled environment. The people running the refinery can say, look, nobody is allowed to operate on this frequency band except for our sensor devices and our actuators. Or Ford can say, look, no Wi-Fi devices allowed on the floor. They can control kind of what that environment is like in terms of the networking. But they really care about high reliability, control systems. So these are very tightly engineered controlled systems. In contrast, we have home area. The different class of networks is home area networks. So these are sort of similar in that you want to be sensing things about your home and maybe turning on lights, et cetera. But these are consumer-grade devices. This isn't a house. You can't control what people bring in their house. You have hundreds of them maybe in your home. These things have to be much cheaper, so you want to use unlicensed spectrum that raises all kinds of issues. How do you make it work when somebody puts their Wi-Fi device right next to it, which just blasts out the spectrum? But these are stationary devices sensing and interacting with an environment. The next class are personal area networks. These are when we see these fitness trackers, all these things that we wear that connect often to a mobile phone, a gateway, to get broader internet access. So these are things which are stationary in terms of the network. Like I have a single phone I'm walking with and these things interact with it, but then they're moving through a physical space. So depending on where I am, my phone might or might not have connectivity. I might be interacting with devices around me, sort of my personal area rather than the home area. And there's just a couple per person here, right? You can imagine these are things which have a long-lasting relationship with me. Finally, you have network devices. So these are things which look like IoT, neat embedded devices, but are basically Linux PCs. So like a Nest thermostat, that's a Linux PC running behind that neat interface. And so they raise all of the standard security challenges that Linux raises with anything of that degree of complexity. The number of lines of code running on your up bracelet is several orders of magnitude smaller than what's running on the Nest thermostat. So those are actually the internets of things. And so when people use this term, depending on who they are, they mean some subset of these. And that's why it can sort of be confusing as to what are the problems and what are the challenges. But I think one interesting thing that comes out from all of these architectures, and this is something which actually a grad student last year just sort of started surveying the space and had this great insight, is that all of them, despite their very different requirements, their very different environments, their very different scales, all of them share a similar architecture that looks like this, which we started calling the MGC architecture, sort of a joke on MVC, model view controller. So the M are the embedded devices. These are these often small, but sometimes not, your refrigerator, but these are the actual IoT things. Then we have gateways. And gateways are some thing that's plugged into the wall from Cisco or your phone. These gateways can talk to the embedded devices using some low power, home area network, personal area network protocol. And they would provide access to the broader internet. So for example, phones, you're going to talk over Bluetooth Low Energy to your Fitbit, but then use LTE or other 4G technologies or 3G to talk to the cloud. And then you have the cloud, so things running on servers, applications, big data stores, analytics, et cetera. And so you see that these applications, by and all, they all have this architecture. We have our embedded devices, our gateway devices, and our cloud devices. And so one of the reasons why building these systems is so hard and why I think their security is today such a mess is if you look at how the code, what you write these systems on the left in, you're basically writing them in C, some low-level systems language. You want it to be very resource efficient, very small. So you write custom embedded software in C. Then when you write the gateway code, you're writing your gateway code on iOS, so like in Swift or in Objective-C. You're doing Android, so you're using Java. So you're writing then the code on the gateway in a completely different language, on a completely different processor architecture. And then when you get to the cloud, the same is true. You're writing something in Rails or PHP or Django or Node. So you're suddenly now writing your code in Ruby for Rails or JavaScript for Node or PHP or Python for Django. And so what this means is that we have not only 3 different classes of devices running 3 different processor architectures, right? Whether it's like a microcontroller, then an ARM processor, then an x86 processor, with 3 different languages, 3 different operating systems. I mean, writing applications is hard. Writing these kinds of complex distributed applications is even harder. Not to mention all of the networking protocols that are in there that somehow you have to deal with. So the whole point is this is amazingly complex. It's distributed systems, and it's no surprise that security is such a nightmare. You have 10 to the 6 difference in resources. Like the things on the embedded devices have kilobytes of RAM. The cloud servers have gigabytes of RAM. And while just developing these applications is hard, I mean, securing them is nearly, it's almost impossible. Just think of the size of the attack surface. If I can compromise any one of those parts, I've compromised your application. And that's, in different languages, different operating systems, it's a total mess. Furthermore, today, our threats for web compromise are people still, okay, there's still personal information that's valuable, like my social security number, identity theft, or there's still credit card numbers. Okay, there's fraud, that's a problem. But think going forward, this is going to be very, very personal data about where you are on a minute-by-minute basis, or what you're doing. This is, can be not necessarily possibly medical, but also even sort of pseudo-medical in the sense of fitness data. So this is going to be data very, very personal to us, which suddenly, if compromised, people will be able to get it. So today, gosh, a server was compromised, and then they stole my credit card number, and then the credit card company, gives me a call. Tomorrow, the server is compromised, and now organized crime is selling when I'm going on vacation so people can break into my house. And the challenge here is that right now there is such a push for these applications. Like you're reading all of these news stories about the Internet of Things, it's taking off, it's going to change the world, it's the next technology revolution. And that means that everybody's rushing to capitalize on this opportunity. I think Chris Ray commented to me that he read some stat that 45% of developers now are developing, or sort of, just hired developers are developing IoT applications. So there's this rush to develop what's seen as this next new frontier of the internet. And you know what? If you have a hard problem and people are rushing to solve it, they won't. And so the idea is like, oh, let's just avoid this problem. Let's not worry about security. Let's just deal with it later. This is what happened with the web. And we've seen the implications of that. So the goal of the Secure Internet of Things project is really 2 goals. The first is data security, which I'm going to spend most of my time on today, which is to research and define new cryptographic mechanisms that will allow us to do secure data analytics on the streams of data we expect from the Internet of Things. So let me explain what I mean by this. So fundamentally, security is about limiting what you can do. If we can do anything, then the system can just be cracked easily. And so the question I want to ask is, what do IoT applications need to do? And if we constrain them to do just that, then in theory, they'll be more secure. You won't be able to work outside the box of what's possible. If you look, many of these applications are seemingly somewhat straightforward, right? With the exception of the third bullet. Just you generate some data samples, you process or filter them because you don't want to send tons of data. Power is valuable. You don't want to sort of limit the communication that's needed on the edge devices. You get them up into the cloud somehow. You do some analytics. Like we'd like to, for example, based on the fact that you walked this particular hike and you really liked it, maybe give you some recommendations to other hikes you might like. You can combine things like your rating of that hike or your enjoyment, the speed that you took it, what your heart rate was, whether it was a good workout, within a GPS trace of it, and from that, sort of like the Amazon recommendations for the fitness-minded. And then we're going to produce some results for an application review. So it'll tell you like, hey, you liked walking on Mount Tam, maybe you should go try this hike on Mount Diablo. And so our goal here is to have something called end-to-end security. The idea is that the embedded devices, like my fitness tracker, my phone, et cetera, are going to generate encrypted data, right? So data that is confidential. And it's not until the data reaches the end user application, so the recommendation of like, hey, maybe you should try walking on Mount Diablo. It is not until then that the data will be decrypted. But yet, the cloud and the gateways are going to be able to operate on this data and do the kind of processing necessary for those recommendations without knowing what the data is, without knowing what the result is. It's this idea of computing on encrypted data. So this might seem to some people in the audience like kind of like ridiculous and impossible. Others might say, oh yeah, this is totally possible. But I was going to give the brief background because the idea that you could do this, that you could do what's called fully homomorphic encryption. You could encrypt something, you can do arbitrary computations on it. It was something that was first proposed like as an open problem in 1975. And then actually a Stanford graduate student answered the question in 2009. So Craig Gentry, who's here at Stanford. He now works at IBM. He received just this year a MacArthur Genius Award for his result. And so the basic result that Craig demonstrated is that we can take some data, encrypt it, perform arbitrary computations on it without knowing what the data is and not knowing what the result is. And so it looks like this. So I have a device, and it has two sensor values, let's say 10 and 7, and it encrypts them. So they just become these black boxes, X and Y. It sends those values, X and Y, to a server. The server doesn't know what they are. There's black boxes. The server can perform, say, a multiplication on them and produce the result XY. It then returns that encrypted result XY to the client, to the device. The device can decrypt it and get the answer 70. And so what we can have is this case where the server has encrypted data as an input and encrypted data as an output. It has no idea what the result of that computation was, but it can perform that computation centrally with all of this data. So this seems like an amazing, amazing result, but there's a catch. So with this result, we could say, aha, we can do any analytics we want. We could do any computations, any data science on these streams of data that we want. So that's true. It's possible, but it's not practical. The overhead of this is more than a millionfold, in the sense of to do a multiply is the equivalent of having to do a million. And so it's not practical to do fully homomorphic encryption, that is arbitrary computations on data. But, and this is where the research lies, it's been demonstrated that you can do particular computations quickly. So I can design a crypto system, for example, in which I can practically do linear regression on encrypted data. So I don't know what the input data is, I don't know what the output of the linear regression is, but I can do the computation in a practical way. And so I think one of the big questions that we're starting to tackle is, can we compute statistics? Can we do analytics on secrets? So answering questions like being able to compute what percentile you are in water use without knowing even what your water use is. Or telling you, say, what your energy use is compared to your neighbors without actually knowing what your energy use is or what your neighbors are. And so there's a bunch of different mechanisms we can do to achieve this. There's not just homomorphic encryption. There's also things called like distributed computation, where I never reveal my value and nobody ever really reveals their values, but somehow in some distributed fashion, without having to stick all of the data on a server, we can still compute an aggregate result. Right? So I can know the results without ever knowing what the intermediate data is. This is an example of I'm playing a game with my friends about, say, weight loss or some other, who's saved more water or whatever I want to do. And we can together compute some results in a very efficient way without requiring a central server. But we've only started to scratch the surface on what we can do. So we can do linear regression, we can do some forms of machine learning, but there's a lot out there which we can't yet do, which we don't have crypto systems for. And so one of the big goals of this project is to figure out what are the computational models that we need? What are the operations we want to perform on these streams of data? And if there are a couple common operations we want to perform, then we can design crypto systems for them, and we can do them securely while maintaining privacy without revealing the data. And so there's this whole open question of, based on what analytics we want to do or what kind of data science we want to do, how are we going to build the crypto systems for them? Great.
Question?
Yeah.
So for the homomorphic encryption, you said any computation?
Yes.
Can you do like x plus 5?
Yes, absolutely. So the point is homomorphic encryption was, it's easy to, there are systems where you can do plus, there are systems where you can do times, and this is the first system where you could do plus and times. And if you have plus and times, you can do any computation.
But
right.
My 5 is not encrypted, it's just, I'm just saying x encrypted plus something that's not encrypted.
Well, I would encrypt the 5.
But
right.
You don't have the key.
Oh, you want the server to encrypt
yes,
the 5?
Yes.
Yes. So there would be ways where you might have ways to translate value. So there are ways you can set it up such that the server doesn't have the key, but they have a way to encrypt something encrypted with their own key and turn it into something encrypted with another key. And so what I would do is I give you a transfer function where you can take your value and then you can encrypt it, or I can do a one-way encryption. So you can produce an encrypted value that doesn't necessarily mean that you can decrypt it, right? Of course, this would raise you into issues of where you might want to, one challenge that arises there is, if I can know what the value of 5 is, if I did a trivial encryption of just a one-to-one mapping, say, then I could just enumerate all of the values and I could start guessing your values, right? So there are absolutely issues there. So, yeah. Any other questions? Okay. Great. So the goal here is that we're going to be able to perform analytics on encrypted data. And so you imagine if you're someone like Nest, this would mean that you can do all kinds of learning on the sensor data from a home, but if the Nest servers are compromised, the data is encrypted, right? The adversary will get nothing. But we can define these computational models. This would be great. We have these building blocks, but we also want them to be adopted. We actually want to have impact. We want this to change how people build systems. And so the second part of the project is system security. And so the idea is let's build a software framework that actually implements these models, that makes them easy to use, so people can build an IoT application as easily as they build a web application today. In 1995, it took 10 people 2 years to build a web application. Today, it takes 2 people 3 months. We'd like to see that for the Internet of Things as well. And it turns out that the state of the art in system security on embedded systems, on IoT systems, is pretty dismal. So I won't go into the sort of the details exactly what this is technically getting at, but I think the important point is that last sentence, that like free RTOS. This is the RTOS that's running in the Nest Protect, for example. It just makes this assumption. There's no malicious code, right? Like there's no adversaries here. Like we'll encrypt what we send over the network, but there's just this whole model that you have complete control of the system, which going forward is not feasible. As we see any kind of new platform like the phone, right, the iPhone and its app store emerges, we want to be able to load applications onto them. We want to be able to do so securely. And so the current, what we've got today is not going to let us do that. And so as a first step towards this, one of the projects, so the research projects within the larger project is a new secure operating system for IoT devices. The idea is if we're going to make these systems secure, we have to start at ground zero. We have to make the edge devices secure. If they're not secure, all bets are off. And so a few students, this is a collaboration between Stanford and Michigan and UC Berkeley, are building a new open source secure operating system for these embedded devices based on ARM's Cortex-M family, which you see sort of in every, say, iBeacon or BLE tag today. So this sort of become the dominant processor. And it uses a mixture of techniques from all these different parts of computer science. So we're using hardware isolation to protect code in some ways, protect you from maliciousness, software, languages. So using really in 21st century CS techniques to make these low-level systems secure. Right? Today, most embedded systems are in C. That was a language that was written 40 years ago. We think and we know that we can do better. But ultimately, if it's hard to use security, people will circumvent it. Right? Convenience versus security, people will always choose convenience. And so one of the key, I think the big challenges for us is that security has to be easy. It can't be that doing the right thing is hard and therefore everyone always just does the wrong thing. And so you see this all the time. We see this in the IoT devices that HP looked at, where they just send data in the clear. Because you know what? Actually setting up an SSL socket's a little harder. And so let's not worry about it. Right? Let's hard, pressing needs. Let's deal with it later. But to make it easy, we have to know what the development model is. Like easy for whom? Easy for how? What is hard? What do people encounter? And so what you see in these IoT devices, because they're things that often are directly interacting with people, they're things that are sort of recognizing our gestures, or they're things that we wear, they have sort of a degree of physicality and interface, which a lot of traditional computing systems that we're used to, like a laptop and stuff, doesn't. And so what we see is as people develop these systems, what they do is they have this rapid cycle of prototyping, modification, and wanting to take these systems and quickly evolve them. We see this in efforts in the D school, the whole rapid prototyping and multiple prototyping approach. And I think one of the big goals of the project is we want to figure out how can we make this concept of security accessible and understandable to end users. People who aren't security experts. Like today, what do? You hire a security expert and they secure your application. When you have hundreds of thousands of developers trying to do that, diffuse, like two people for 3 months, that's not feasible. And so what we need to do is design this system so that it's easy to understand the security implications of what's going on, and also easy to maintain them. So people aren't just commenting out the things that are throwing errors because there's a security violation. Which happens, anyone who's developed a Rails app and tells you, oh, you have some security problem, you comment out that line in the configuration file, which tells you this happens all the time. So one approach we've been looking at for this is a system called fabryq, which is done by a grad student here, Will McGrath, advised by faculty at Berkeley, Bjorn Hartman. And the idea of fabryq is that you want to make it really easy to prototype these applications. Rather than having to write code on the embedded C on the IoT device, and then write gateway code in Java, and then write cloud code in Rails, what they really do is just merge all of this together into one approach where it looks like you're writing a single program somewhere, and then it's just calling out to the different parts. So suddenly, if they can just secure that one piece of code and secure the code that doesn't change on the edge devices, suddenly security becomes much easier to understand and reason about. I just care about securing this one piece and its interfaces rather than all these complex pieces. And so Will is going to be, or actually, he already gave the talk. He moved his date forward, so I'm sorry, he will not be giving a talk on March 2nd. So another approach, and this is one which a postdoc here, Laurinas Riliskis, is investigating, is to take these IoT applications and write them as this data processing pipeline. So something very much like you see in web applications today, model view controller, with the idea of adding this concept of a transform. It's the thing that lets me transform data from one model to another. So for example, my edge device is sampling at 10 hertz, and then I use a transform to turn that into a more meaningful value than just an accelerometer reading. Then from this activity of what I'm doing, say, am I running or am I walking, I can then, over time, process this to a better estimate. Like just because I stopped running for 3 seconds doesn't probably mean I stopped running. It's just a glitch in the data, so you can smooth things out. But the idea is by describing the application at this high level across the entire system and all of its devices, that we can actually start to make claims about end-to-end security properties and what computations are needed, and therefore what crypto systems we need. So why now? You could say the Internet of Things, people have been talking about it for 10 years now, or 15 years, depending on whom you count. Why should we try and secure it now? Why should we care about the data science on these systems now? Well, I'd argue that the technology has reached a tipping point. So it was at this point, 9 years ago, ARM came out with the Cortex-M series of processors. And when they did, they basically were not usable for these low-power embedded IoT applications. They had sleep currents in the order of 500 microamps, which means you can't last very long on a small battery. But just in the past 2 years or so, that 500 microamps has become 500 nanoamps. which means that you can really build things that will last, devices that will last for years on a coin cell battery. And so we have the processors that will let us build these applications in a way we didn't even just 2 years ago. Second, we have the emergence of a networking technology that is going to actually let these things reach the internet. So for a long time, people were talking about Zigbee and 802.15.4, but for market reasons, those things didn't take off. But about 2 years ago, Apple introduced iBeacon. And while iBeacon is not necessarily super important, the fact that this means that now all smartphones, first it was the high-end ones, but now all of them have Bluetooth Low Energy, this amazingly low-power, efficient protocol for interacting with devices around you, means that we can build these devices and we can connect them to the internet. Furthermore, driven by the phone market, sensors, their energy efficiency has increased by orders of magnitude, just driven by the power constraints of phones. And what I think is especially exciting about this is that when people first started talking about the Internet of Things and hardware and software, how are we going to build them 15 or so years ago, we started tackling all of these problems. But the technology wasn't there yet, and now the technology is here. The research community has been waiting. We've been waiting for this day when suddenly the devices we always knew were going to be there are there, and they are. And so we have people on this project who are leaders in how you prototype devices, cryptographic mechanisms, low-power hardware, low-power software, and analytics. But the thing we still don't know, so we now know we can build these systems, is we don't know what the threats are. We don't know what the attackers are. These systems aren't yet widespread. And so we have to explore that and figure that out. So on one hand, the technology has reached the tipping point. We now have this tremendous opportunity. This day that many of us have been waiting for to come has come. But I think as actually Steve once pointed out, the other side of that is it's not too late. That think of this again as like this is the World Wide Web in 1994. Right? It's there. We know it's going to be big. We know it's going to have a profound impact. Nobody's really sure yet. And the big applications aren't there yet, right? Larry and Sergey I think they hadn't gone to grad school yet, right, at that point. And so because the big applications aren't there, because there aren't entrenched applications and code bases and approaches, this means that if we make progress, if we really change the state of these systems, it really could change the state of what the Internet of Things is like in 10 years. And so while it would be great to repeat all of the mistakes of the web and the security nightmare that it is, it'd be great for publishing lots of papers. If we want to think about positive impact on the world, maybe we should do better than that. And I think today we talk about data science, and there's been, I think, a whole bunch of great talks about often gathering data from the computing domain, like blog posts or social networks. You see, this is data about the physical world. And the question is, what is the data science that we're going to do on this physical data of embedded networks? So I'll talk about just a couple of applications, give you an idea of like why this is different and why I personally think this is super interesting. So this first one is something that was published on PNAS. It's now Proceedings of the National Academy of Sciences 5 years ago. And so this is, remember this back then, 2010, so this is like post H1N1, right? There's the H1N1 thing, the super issue, like, gosh, are we going to close schools, quarantine, all these questions of the outbreak because the disease was so harmful, especially to kids. And so if you look, epidemiology is the study of the spread of diseases. And often what epidemiologists would do to understand infection vectors and what propagation might be like is they have graph models of how people interact, how diseases might spread. And these are based on some simple mathematical models like power law distributions or surveys, like write down on a piece of paper, who are the people you talked with most today? Tremendously noisy data, not actually grounded in quantitative measurement because it wasn't really possible to measure. So a couple of grad students working with me teamed up with some faculty here in epidemiology and now somebody who's faculty at UPenn to say, look, if we have tiny wireless devices that can measure when they're close to each other, let's just give one to every single student and every single staff member in a school. And then what we'll do is we're just going to measure whom they do talk to. What does that contact graph look like? Let's not use a model. Let's not use a survey. Let's just measure it. And what does that look like? And so getting a really precise data set of what a real contact graph looks like in a school over a day. So we got 94% of the school to report. It was 788 people. Of course, this is this physical data, so it was totally noisy. There's all this mess in it. It took us a couple of months to clean it, to actually make it usable for some analysis. Things like nodes would reboot, their timestamps would break, we had to reconstitute the graph. So there's a bunch of computer science work in cleaning the data. And then the result was, the actual results from this observation was a top-tier scientific publication that really sort of broke ground in terms of how epidemiology should measure these things for disease transmission. And Marcel was telling me just a couple weeks ago, gosh, today, like, this is the approach everyone uses. Like today, people are now building new hardware, little tags that are coin cells, because this is how sort of the future of measurement and graph and understanding of propagation is going forward. But what's interesting is the security here, because this is 5 years ago, was, OK, we have all these devices, we have the graph. Well, the names of the participants, we're going to just put that in a safe. That was our level, that was sort of IRB level of security. We didn't have any other approaches. Students, staff had no way to look at this data. We had no way where they could query about themselves, or because we had no mechanisms to do so. It had to just be behind closed doors. So another application where I think this is another thing with the same graduate student, but this is her dissertation, for the Internet of Things, was sustainability. And so this is the monthly bill Gates Hall, computer science building, would get. And so there's the electricity bill, $36,000. So just so you know, that's how much Gates Hall consumes in a month on electricity. And you go to the departmental manager, so where does that go? How much of that is computing? How much of that is lights? How much is... No idea. This is all we know. And so we have no way to reduce, as Lord Kelvin said, like, the only way you can improve something is once you can measure it. So if we don't know where that's going, we can't measure where it is. We can't improve it. We could just be throwing darts at a board. And so what the student did was deployed a 200-device IoT system throughout Gates Hall, measuring plug loads on a wide variety of devices, using some really intelligent sampling strategies to try and actually cover everything, and then using some statistical approaches of sampling based on, say, we observe what kinds of devices are plugged into the network. From a computing perspective, she was able to compute this graph. So this is the energy consumption of Gates Hall over a week. And I promise students do normally show up on Mondays. It just happened to be a holiday that week. That's why there's not much of a bump. And what you can see is that the computers in Gates consume 56% of its energy. Right? So over half of the building's energy goes to computers. And a lot of that's servers in the basement. But you can also see, like, the LCD displays follow this diurnal pattern of people coming in, their screens turning on. You can see the little dip that is lunch. And that increase of the LCD displays is about half of what the daily increase is during the middle of the day. So the LCDs are about half of what, are about equal to what the lights are. So people come in the offices, turn the lights, and the LCDs are about equal to that. And so based on this, we could then start making really clear recommendations to the department about how it could save energy. And so you had a bunch of policies, a bunch of approaches, ended up having some good effects. For example, after this study, we just saw the tremendous difference between laptop and desktop energy performance. It's now, when new students come to Stanford, the computer store, its web page lists the laptops first because they consume so much less power than the desktops. So another application, and this is one I'm working on now as part of this flagship grant, and this is with Noah Diffenbaugh in Earth Sciences, as well as a few people in computer science and electrical engineering, Mark Horowitz, Yuri Leskovic, Chris Ray, and Dan Bonnet. And then 2 students, Holly Chang and James Hong, and the postdoc Larinas, is today, like 5 years ago, we were concerned about electricity in Gates. Today, California's in a drought. And we know how much water Stanford uses, but again, it's sort of like that energy bill. There's just this one line item. We don't really know where it's going or why. And so what we're doing is we're building an embedded sensing device, which we can install into any water tap, into any faucet or shower. and it's powered by the flow of water. There's a little generator in there because these things don't require much power. And what it's going to do is it measures the temperature and the flow rate of that tap. And the idea is that we're going to actually gather on like a per spigot basis within, sounds like most of Stern, as well as a few other dorms, where is water spent in the building? And also when is it spent and how is it spent? These devices can't transmit far, so we have a data mule architecture where phones running applications will then pull data off the devices and send it up to the cloud. And so the big question here is, we're going to be able to collect all of this data. What we would like is to be able to send messages to students. Are there interventions we can make, like, hey, you actually used a lot of water today, or you left this tap on, or perhaps turning the temperature up in a bathroom because warmer bathrooms lead to shorter showers because people aren't cold. But we want to be able to do these kinds of pattern detections, these kinds of interventions without necessarily violating student privacy. It would be kind of neat if all the data on the server, it generates results and it doesn't know what the results are and sends things to students, doesn't know who, such that even if the server is compromised, we haven't suddenly told somebody exactly when every student takes a shower. And so figuring out the exact algorithms to do this, this is what we're doing right now to make the system secure. And so in summary, the goal of this project is really about gathering the data. This notion we're going to have these Internet of Things systems that gather data for analysis and for analytics and for data science. The low-level technology has reached this tipping point. We know we're going to be able to collect these huge streams of data, but the privacy and safety implications of that are tremendous. And so the question is, can we just do it differently? If we just turn the crank and repeat the web, we will have all of the same problems. And so what we want to do is, before that day arrives, attack this problem head on, so looking forward. And so the idea is that in the future, we'd like to be able to do not only impressive data science that allows us to improve sustainability and energy use and make good observations about disease spread and all kinds of applications that touch the physical world, but do so in a way that doesn't violate privacy, that's secure, and easy to deploy. And so in that light, I'd like anyone here who's interested in applications, wants to build these kinds of systems, we're a resource for you. We want to work with applications people. We want to develop systems. If you have an idea for an application you'd like to deploy, you want to collect data from the physical world and then do analysis on it to reach, have better science or deeper understanding, we would very much like to work with you. We want to know what kinds of computations you need to do. We want to be able to make it so that you can do them securely in a way where things like IRB approval are much, much easier because, gosh, the data is never revealed. It's always secret. And that not only does that protect all the measurements you're doing, it also allows you to sleep easier at night. So with that, I'd like to take questions.
If you are thinking about the implication of the water sensors to agriculture instead of urban use?
So we haven't yet. In terms, so we haven't yet, would be the short answer. We were mostly thinking this is very much like, hey, we'd love to deploy something here at Stanford, make a difference. I think that this application would totally be valuable there. I suspect that sort of depending on your scale of agriculture, like if you're talking about watering whole fields, you know when those sprinklers are on. It's not, like you already have your control system. And so if it's already a controlled irrigation system, there's less of an issue of gathering data, but it would allow you to do things like detect when there are leaks, right? You can see that there's a flow. So, but yeah, that's a great point. I mean, our goal is open source everything. Like, sure, if people want to use this, use the software, use the devices, would be absolutely great. Yeah, partnering with people doing that would be totally interesting. Yeah.
What kind of sensors does your software support, and what's the process for making new ones?
What kinds of sensors? Well, so at the low level, like any sensor, right? You can interactive, robust, and create like. Today, writing drivers for every single sensor chip out there is not a good use of grad student time. So we're doing it very much on a demand basis, right? Like, so for example, the water sensor basically has a thermistor to measure water temperature, and it just has a Hall effect sensor, so a magnet, right? So it's like magnet spins, and you see a spike of voltage, and the magnet goes by, so you just count the spikes. So two very simple sensors that'll let us do this. And so it's very much a step-by-step process. There are hundreds of thousands of sensor chips, and we can't. But each one is not hard to do, but you just need to just do the ones you need.
Is there any kind of like common interface that like
No.
no?
Unfortunately, no. Right. So there is in the sense of like the bus. Oh, this is an SPI bus. But like
Yeah.
every sensor does its own thing. You send little commands. Yeah.
I see.
It's like totally not standardized, which is why not writing libraries of it is a terrible use of grad student time. So, yeah. Any other questions? Are you scared? I'm scared of the Internet of Things. You will be, unless we, make some success. So.
So do you have any ideas about the ease of use? Because that's been my, and you mentioned it, the intense frustration with security. It's just like always in the way.
It is, right? And why? It just seems ludicrous. So I don't, with the exception that I think. So there's certain things in the internet where it was built with this model that everything can talk to everything else, and therefore when it can't, everything breaks. I've gotten a bit better about that, just understanding there are those limitations. But I think it's also, if you wind back, user interfaces 10 years ago were not designed by user interface people. They were designed by engineers, and that's not necessarily how you want things to work. There are plenty of systems today where people are coming up with UIs that are so much easier to use because people who are actually experts in that are now designing the UIs. For example, I have one of those little wireless headset things. It's the one from Jawbone, right? It's the Era, I guess. And I took it out of the box, and there's like no instruction booklet. I'm totally confused. I'm trying to figure it out. I'm like loading up the instruction booklet on the web, whatever. And it says like insert into your ear and turn on. So I insert it into my ear, turn it on, and then it starts talking to me. It gives me the instructions. Like, oh, this is really easy. So like, take your phone, open up the application. Like, oh, I'll wait until you open up. This is such a better user than like reading a manual. So I think we are going to get progress there. And this is actually why I think Bjorn Hartman, does prototyping and user interface, it's absolutely critical that he's part of the project to understand what are the cognitive models that people can think of and can reason about that are simple and easy, but actually enable them to do useful things. So we need experts in that. Otherwise, it won't be any better, and we want it to be better. Any other questions?
What about metadata?
What about metadata?
Yeah.
That is a great point. So it turns out, for example, in this water application, that we're going to measure these faucets at these times. That's not very sensitive data. We'd be less concerned about that. But then the data of, this phone was in the bathroom at this time, and it's the one that data muled this data from that metadata. It turns out the data we need to collect to monitor the system to make sure it's working correctly is far more sort of privacy prying than the data of the system itself. And I think that is a really interesting and difficult challenge in the sense of the data you gather, okay, we can protect that. But then when you want to do the system monitoring, is it working? That stuff turns out to be, the privacy there becomes much trickier. Because I want to know, for example, this phone seems to be taking lots of data off the devices but never reporting it. There's something wrong with that phone. At some point, I need to talk to that person. So now privacy, there's a sort of a privacy battle there. Of course, you might send them an anonymous message and see if they get back to us. But at some point, wait, we want to debug it. Is there a bug in our code? So great. That's actually where, the data itself, we can protect. The real challenge, I think, is going to be in the metadata and what sort of things we need to do there. Great point. Yeah.
How effective do you think the data privacy technique and building statistical machine learning to be valuable?
So I didn't quite get the beginning of the question.
Do you think the data privacy method using machine learning and statistics?
So data, do you mean if I use machine learning, will I be able to break the privacy? Or?
A lot of algorithms based on different privacy.
Right, so differential privacy is a little different, but I think people have demonstrated the ability to do machine learning algorithms on encrypted data. So the idea is the algorithm doesn't know what the data is. It has no sense of what it means through strong cryptographic statements as to what that is. It has no idea what the result is. And so at that level, you are absolutely protected. Now, whether or not you could figure out something from the timing of data, those are sort of the metadata side channel things, which might be, I think, an issue. For example, even if we sort of keep all of the data on a floor confidential, like about water use, et cetera, at some point, we're going to know something about what happens on a given floor, right? There's this notion of that's the level which we want to examine the data, and that's going to say something, right? If like one floor never takes any showers, we've learned something about that floor, even if we haven't learned something about an individual person. Right? So even when you're doing aggregate results. I'm not sure if that answers your question. From your face, I think no. But so maybe if you ask it again, I'll understand it. So.
But just like there are some like research showing like even though you prevent people from asking like an individual question, there's still ways to attack. You can ask about the like.
Oh, I see what you mean. Yeah. So that is a point of, gosh, the server has the truth, and we're now limiting what questions you can ask. But then maybe if you finagle the questions, you can still figure things out you weren't supposed to know, queries. But at this point, the server doesn't know the answer, right? Like only the client can actually get the answer. So it's not the differential privacy approach where we're going to have the server limit what questions you can ask, but rather the server can't reveal something it itself doesn't know, right? So, but you're absolutely right in the sense of when then people can ask questions and they get answers to them which they decrypt, differential privacy is absolutely an issue. In the sense if I can like figure out who it was that was showering at a certain time, that would be really bad. So, yeah.
So for this encrypted computation thing, the key is stored on the client for each client.
That is one approach. Yeah. Right.
What happens if you lose your phone? What happens to your data? Can you get it?
Can you get it? Well,
Can you get it back?
Can you get your data back? So the sense of like I've lost my phone, which then means
lose the key.
So I lose your key.
Well, I mean that's
there are all kinds of techniques for key recovery, right? In the sense that we can do all kinds of authentication to actually get you the key back. Yeah.
So you reflected on the web and all the insecurity. There are epics before that too, right, with computers. I mean, as you did time sharing and such.
Yeah.
And a strategy that emerged over incrementally was really trying to create pretty secure barriers, whether they were virtualization or a kernel, and then there was capability architecture, there's a whole bunch of different struggles. Has there been any thought of extending paradigms like that to distributed systems where you create kind of capability lists of who can touch this data, who this data can talk to, who it seems like it could be something there.
So the answer is yes, and I think the approach that really has seen tremendous success there, and one of the folks on the project, David Mosier, is one of the leaders of this. It's one of information flow control, where traditionally computer systems have really looked at like, oh well, you can do this but not that. Like you can open this file but not that file. And instead, so these sort of you can imagine as executive or operational things of what you can do, what you can't do. Instead, information flow control says, look, let's not care about any of that. So we're going to say, what data can you write? What data can you read? That is, you talk about security in terms of the data. And what will happen is, in an information flow control system, is you can, for example, say, look, you can either write to the network, or you can read the password file. But I can enforce that you never do both. That there's no way that information, you basically can set up a system where information cannot flow from the password file to the network. And the system just has to enforce that. It doesn't know what a password file is, doesn't know what the network is, just that there are simple labels. And it says, well, you have label this, and you can't have these two labels at the same time, you go kaboom. You're shut down, you try to write to the network, and I'll just tell you, sorry, too bad, right? That's not allowed to propagate. And that has emerged as a really effective way to protect data and its flow through a system. And people have done that for distributed systems, absolutely. It's a bit tricky because often it's this example of it is an amazing technique that is super clean, super effective, and super hard for anyone who doesn't work in that space to wrap their head around. So one of the big results in that space was this operating system called HighStar, which used it at every single level of the operating systems, like just your system, like literally this network password file thing. The student who wrote that paper was a student here. He's now a tenured professor at MIT. But you read that paper, and wow, it requires several times to understand exactly what is happening because it's not something we usually think about. Once you get it, oh, it's clear, right? But it wouldn't be something that's accessible to two people working for 3 months. And so can we somehow make it easy to understand what's happening? That's, I think, an open question that David is really interested in looking at, has started looking at.
because it really would create different types of operating systems in these environments, where you're not just worrying about sharing resources, you're actually worrying about almost having access control on operations. It can create a very different environment.
Yeah, I think so. I think that's very, very right. But I think it's also, let's just think about not just the operations, but about the data. Like, I don't care that you read. What I care is what you read. Okay, great. Thank you so much.